Hello everyone. In this clip, we will continue on making an inference. From last time, we talked about statistical inference, and there are two ways to do it. We do hypothesis testing, and we do parameter estimation. So in the next section, we will talk about the parameter estimation right here in the red box. Okay, this guys. All right, and the first way is to estimate the parameter. Remember, we are looking at the population parameter, and in this case, in this example, we are looking for the average weight of the population. By doing so, we take a sample out, and then we will make an estimation of the weight of the population. Okay, so in 4.3 we will talk about parameter estimations. It is a method to make an inference. Okay, a parameter estimation, it is a process in which we select a random sample from a population and use a sample statistics to estimate the population parameter. Okay, so we use a sample statistics. For example, we use sample mean, sample standard deviation, sample variance, proportion, or whatever to estimate a population parameter, right? For example, the mean. Okay, we are looking for population parameter, but we cannot measure it directly, so what we do is we measure in the sample, then we make an inference about the population. And there are two types of parameter estimation. The first type is point estimation, and the second type is interval estimation. Okay, so in 4.3.1 we talk about the first type, which is point estimation. And with this method, we estimate a population parameter by using just a single value in the sample. Okay, we use just a single value. Okay, use just a single value in the sample, okay, to estimate population parameter. For example, e.g., for example, population means, okay, here, if we use mean of a sample to estimate a population mean, then we do this. Suppose we take out a sample and then we find the average weight, and which is 62 kilograms for this sample. Then for point estimation, we just use this value to estimate the population parameter. So we use exactly this value from the sample as the population value, as population parameter right here. So we say that, oh, the average weight of the population would be 62 as well with this point estimation. Okay, just use just a single value of the sample. For example, back to our example before, where we take the population has 4 data, and we take our sample of 2, and we have 16 sample, right? 1 2 3 4 5 up to 16 samples. Okay, remember that. And with population mean of 158 comes from here, find the mean of this. Now if we consider this, take out the first sample, which is I think take out this one. Okay, sample 1, if I take 152 and 156, the sample mean of these two is 154. Then with point estimation, okay, we just use this value as the population mean. Or So the point estimate of the population mean for this example would be mu equals 154. We use this as the population mean. But if I take out another sample, I take this sample 156 and 160, the sample mean would be 158 kilogram, right? And I will use this one as a point estimate, okay, for the population means. So with this sample, I use 158 as the population mean. So point estimate of the population mean is going to be 158 with this sample. Keep that in your mind. The actual population mean is 158. So with two different samples, if you use point estimation, it depends on the sample you pick. There will be an error for sure. So it has uncontrollable error depending on the sample you pick. Of course, because the true value is 158. With this sample 1, you have error. With the second sample, okay, you're lucky, you don't have error. So as you can see, the point estimation is not is uncontrollable and not reliable because we have error depending on the sample you pick. So we usually don't use this method to estimate the population parameter, okay, but it can give you a rough information to estimate. So this one is not reliable, okay, not reliable. All right, with the point estimate, it's not reliable. So we have the second type, okay, the second method for parameter estimation. Instead of using just a single value, we use interval estimation. In 4.3.2, we will talk about the interval estimation. So we estimate as an interval. Here, we estimate the population parameter by using just an interval, okay, so that the interval that indicates that the population parameter lies in. So actually we are looking for example, the interval of a certain value, like interval of weight, so that the population means lies in here, must lies in here with a high probability, with some confidence, okay. And the interval, this interval depends on the sampling distribution, the sample size, and of course the confidence level, okay. And for example, if you take a sample of the weight of CMU undergrad, and it is 62 kilograms with standard deviation of 3.2, then the interval estimation, it's like this. It's gonna be the interval about 62 plus and minus the ASD. So if 62 minus 3.2 gives you 58.8, and 62 plus 3.2 gives you 65.2. So we can say that the average weight of CMU undergrads, the whole population, must lie in this interval, okay, must be between 58.8 until 65.2 with 95% confidence level, okay, must come with the level of confidence for interval estimation. So instead of giving just a point, like point estimation, here we give an interval, okay. So before we move on to the next step of finding the interval estimation, we need some notation here, common terms that we need to use. The first thing is confidence interval, or CI. CI means confidence I means interval. Okay, the confidence interval, what is it? It is a range or an interval of values used to estimate the true value of population parameter. So it is an interval just like this. Okay, the confidence interval and the confidence level. Okay, we have confidence interval, the interval or range that used to estimate the true value of the population parameter, and the confidence level. Okay, confidence level or confidence coefficient. It is the probability. Okay, it is actually the probability of the value is 1 minus alpha. Alpha is significant level. Oops. Okay. Actually, it might be this. Okay, level of significance or significance level. So the confidence level is 1 minus alpha. For example, we say 95% confidence level means the probability is 0.95. This will be related to the C value with the area given in the normal distribution. Okay, and the confidence level actually contain the population parameter, assuming that the estimation process is repeated a large number of times. Okay, we have confidence level. In order to find the interval estimate of the population parameter, you need to give a confidence level as well. They come together as a pack. Okay, let's see. Of course, it is probability. Then it has to be between 0 and 1. Probability. The value must be between 0 and 1. And alpha is significance level. For example, like this. You should be familiar with this by now. This is the normal distribution, example of normal distribution here. And the value on the x-axis is the C value, okay? C value. This is normal distribution. When we talk about confidence level of 1 minus alpha, it means that the area between here in the middle is 1 minus alpha. Excuse me. So, in the middle, if you talk about the population in percentage, this will be 100 times 1 minus alpha percent. Or can take out the bracket. See, it's the same value. This is confidence level. So it's 1, the value is 1 minus alpha. For example, 0.95, 0.90, 0.80. So of course, if the middle is 1 minus alpha, the whole thing is 1, right? The probability, the whole thing is 1. Probability. And if the middle piece is 1 minus alpha, so the two pieces combined is going to be 1 minus alpha. So these two add up to alpha, right? If the middle is 1 minus alpha, then the piece on the side, along the side here, these two pieces combined to alpha. So if these two combined and get alpha, and they are exactly the same, right? Okay, they are similar to each other, exactly the same size, then you split into half. Each one will be alpha over 2, right? The area will be alpha over 2. Let me mark as a red area. Red area is alpha, then one piece is gonna be alpha over 2, and then add up to get alpha. Okay, and the value down here, we have so many values to be considered. And if you look at the z value on the x-axis, the standard, excuse me, the z value here, we call it z alpha over 2 right here. So it's gonna be by looking for the z score, right, from the table, so that the area underneath here is going to be 1 minus alpha and then plus alpha over 2. Whatever it is, you need to look at the area, the whole thing here, and look for the z that is related to this area, and you will get this z alpha over 2 from the table. Okay, from here the confidence interval, we have confidence level. Confidence interval is going to be the green interval here, which is minus z alpha over 2 comma z alpha over 2. So the confidence interval is going to lie in here. Start from here to here. Okay, everything here is confidence level, a confidence interval, sorry. The confidence level is a probability or the area under the curve, okay, from minus z alpha over 2 to z alpha over 2. For example, if you say 80% confidence level, if we say 80% confidence level, okay, this means in the middle piece here, it's going to be 0.8, right? 80%, the probability is 0.8, so that a piece here on the right is going to be 0.2 divided by 2, and here is going to be 0.1, and here is going to be 0.1, right? And up to be 0.2, and then add 0.8 equals 1, right? The way to find it is not hard. You can set up the equation. In the middle piece, this guy is 1 minus alpha, 0.8. So that alpha is going to be 1 minus 0.8. So alpha is 0.2. Then alpha over 2, just one side, one tail, is gonna be half of alpha, right? One tail. This is the left tail. This is the right tail. Okay. Left tail, right tail. Okay, can you see the big picture now? From here, if you want to find the z or z value, what you have to do is go look up the table or use Python. Look for the value, this value, z alpha over 2, so that the area, the CDF cumulative density function here, this guy is gonna be 0.8 plus 0.1, right? 0.8 here, and another 0.1 here. So we're looking for the area, just start from the leftmost until here. Okay, so it's gonna be 0.8 plus 0.1, which is 0.9. Looking for that value that give the area of 0.9. Okay, so your job is to find that such that P of z less than little z of phi A, right? It's going to be, it is 0.9. So looking for the value here, you see this C value. And this, the value that you get, we will call it Z alpha over 2 for the confidence level of 80%. This is an example. Okay, let's move on to the next one. Example of the most often value used. Usually the confidence level, we use 95%, a lot. 99, 90, 95, we use a lot. If the confidence level is 95%, it means that this one, it means that 1 minus alpha is gonna be 0.95. So alpha is swap around, gonna be 1 minus 0.95, which is 0.05. So this is two-tail test, and so that half of this is going to be 0.05 over 2 divided by 2, you get 0.025. So this is one tail. 0.95 is in the middle, area in the middle. We talk about a probability, which is the area under the curve. So one tail is 0.025. This one as well, the left tail, is going to be the same because they are similar to each other, symmetric, right? They are symmetrical about the middle value, which is the mean. So 0.025 here. And looking for the table, look in the table, we look for Z that has the area phi Z such that P of big Z less than little z is 0.95 plus 0.025, which is 0.975. Just like that. How do I get this? I add this 0.95 to 0.025. Add these two together. Okay. And let's see the common values. The common values of the level of confidence or confidence level. The level of confidence can be any number between 0 to 100%. And the most common values are 90, 95, and 99. If it is 90, then alpha, it's 0.1. Alpha over 2 is going to be 0.05. 95%, we talk about that. 99, then what is left off? It's going to be 0.01. So alpha over 2 is 0.005. Like that. And the z-score, we already found it here. Actually, we need to fix this. For 99%, it's actually 2.5. We use 2.575. Okay, fix that. So hope you understand this. For 90% alpha is 0.1, right? It's 1 minus alpha is 0.9, 1 minus alpha 0.95, 1 minus alpha is 0.99, so alpha is 0.01 for the 99%. The z-score, as I said, you need to look in the table. Look for the z value here. You need to add the area just from the leftmost, the left tail, and then the middle piece. Okay. For example, 90%, then the area is going to be 0.9 plus alpha over 2. Alpha over 2 is 0.05. So area is actually 0.95. And look in the table for z value that has the area of 0.95, for example. Alright, we'll be using this a lot. Hope you understand this. To interpret next, we need to interpret the confidence interval. What does it mean? Suppose we have 0.95 confidence interval of the population mean. Suppose we know that the 95% confidence interval is from 0.405 until 0.455. Suppose we know that the mean is between these two values with the 95% confidence. Okay, what does this really mean? This means that we are 95% confident that the interval from 0.405 to 0.455 actually does contain the true value of the mean. It means we are 95% sure, okay, 95% confidence that, oh, okay, the mean lies within this interval. Okay, that's it. This is the meaning of the confidence interval. Okay, we are 95% sure or confident that the mean lies in here. Okay, the population means. Okay, and this is a wrong interpretation. It doesn't mean that 95% chance of the true value falls between this. Okay, it doesn't mean this. It doesn't mean like there is a chance of 95% that the mean lies in here, or it doesn't mean that 95% of sample mean will fall within this interval. No, it doesn't mean like that. It only means that, oh, we are 95% confident that the mean is in here. Okay, different meaning from the last two. Okay. All right, let's see some example of how to find. We are looking for the interval estimation. Okay, don't forget our main goal. Our main goal is to find an estimation of the population mean. Right now we don't use point estimation, but we will give the interval that the mean will lie in there with some confidence level. Okay, so let's see example 1. Find the number find the z-score or z here needed in construction of confidence interval. Okay, A, when the level of confidence is 90%. Okay, we are looking for z alpha over 2. All right, let's see part A. The first example is 90% confidence level, which means 1 minus alpha is going to be 0.90, and so alpha is 1 minus 0.9, which is 0.1. So alpha over 2 divided by 2, you get 0.05, right? We are looking for the z value. So that the area here is, we have tail here, right? So that the area here is going to be 0.9 plus here alpha over 2, 0.05, right? Because the middle piece is 0.9 and the left tail here it's alpha over 2, which is 0.05. So you need to add these two pieces, the yellow and the green one, okay? Which give you, so the area is going to be 0.9 plus 0.05, which is 0.95. And look at the C table. Okay, look at the table to figure out Z alpha over 2. Okay, let's look in the table, i.e. we find A such that P of Z less than A is 0.95. Okay, and from the table, let's look at the table. Let's look at the table. 0.95, 0.95, 0.95. So it's here. Actually, 0.95 is halfway between these two, right? 9495 and 9505. So 9500 is just exactly halfway between these two. These two mean 1.6 and 1.64 and 1.65. So halfway is gonna be 1.645, right? Okay, I take these two values and write down here. From the table, we have P of Z less than 1.64 is 0.9495, and P of Z less than 1.65 is 0.9505. So actually 0.9500 is just exactly halfway here. Therefore, my A is going to be 1.45, right? Because it's halfway between these two. 9.95 is here in the middle, 95. Right? In the middle here, it's gonna be 1.645. So my A is 1.645. So Z alpha over 2 is going to be 1.645. That's the answer. You need to figure out this value so that we can write down the interval estimation of the population mean. Okay, and this is part A. Part B is similar. You can do it by yourself. Okay, so 99%, 1 minus alpha is 0.99. So alpha is 0.01, right? And the area is going to be 0.99 plus halfway of that, 0.005. So it's gonna be 0.995, and look in the table. We have Z alpha over 2 is 2.575. You can go check it out. Okay, 995 995 here. See? 995. Halfway of 2.5. See? 2.575, right? Look at that. 2.575 here. Okay. All right, that should be it. This is an example. Not that hard, but need to be careful with a lot of steps because you need to calculate the alpha over 2 here. You need the green area, add up with the area in the middle, which is 1 minus alpha here. You add these two up, then you look in the table for this area. Look for C value. Okay. All right. If you understand this, I will move on to the new one. A new distribution, which is required in order to find an interval estimation too. Okay. Another distribution is called T distribution or student distribution. Okay. T distribution. What is it? A T distribution. Okay, this is a continuous probability. Actually, it is a generalized of a standard normal distribution. Okay, so the general case of standard normal distribution, and it has similar property to standard normal distribution. It is symmetric around the mean. Okay, around 0 means it means the mean is 0. And the shape is bell shape. So quite similar to normal distribution, but the difference is this. The variable in T distribution ranges from minus infinity, negative infinity to positive infinity. And it has heavier tails. Okay. Meaning that it tends to produce value that fall far from its mean. So heavier tails here. Okay, looks like normal distribution, but the value has more value along the side. And for T distribution, it comes with the degrees of freedom. You need to identify the degree of freedom in order to find the probability. And degree of freedom, we use the notation df. Okay, we use df for degree of freedom, or sometimes we use nu. Okay, nu, nu is the Greek alphabet. Use df or nu to stand for the degrees of freedom. Okay, and as the degree of freedom increases, the T distribution will get close to standard normal distribution. Okay, the higher the degree of freedom, the closer to the standard normal distribution it is. Okay, and degree of freedom usually, or nu, is usually defined as n minus 1. So n is the number of sample, right? Degree of freedom is going to be n minus 1. And if x follows the T distribution, we write like this. X follows T and with subscript of nu. Okay, T with subscription of nu. All right. For normal distribution, it's n with mu and sigma, right? For T distribution, it's just T with degree of freedom. This is what it looks like. Okay, probability, this is t-score. Looks like normal distribution with heavier on the tail. Okay, with degree of freedom here, the one that is flattened out, look at this. It has some gap here. For normal distribution, it's like flattened out, right? here we have some value, some probability here. Okay, the purple color is just degree of freedom of 1 for t distribution. The higher the degree of freedom, the closer it is to normal distribution. Look, for standard normal distribution is in black color, but if the degree of freedom gets higher and higher, look at the green color, it go close to the normal distribution. Okay, with the smaller degree of freedom, then it kind of shift up a little bit. Okay, and the way to find the area, it's similar to normal distribution. We have the table for t distribution as well. This is the table for t distribution. You need degree of freedom to find it. Okay, and we have, this is the common value. Other than this, we can use Python to find it. Okay. With the confidence level, for example, with the confidence level of 90, okay, then look at the degree of freedom. If the degree of freedom is 1, then the C value is 6.314. Okay. This is the T table, the T value, not C, sorry, T table. Okay. One tail is alpha over 2. Two tails, it's just alpha right here. And the degree of freedom is here. Okay, degree of freedom. And confidence level down here. Okay. Alright, we just look at this. And this is alpha over 2. Also alpha over 2, and this add up to alpha, these two, right? These two add up to alpha. In the middle is 1 minus alpha. Same thing here. For example, find the critical value t of alpha over 2. Which is corresponding to a 95% confidence level. Given that the sample size is 15, that means it gives you the degree of freedom. Okay, we are looking for t alpha over 2. All right. So what we are looking for is T alpha over 2 right here. So we need to find the area, degree of freedom and stuff. This is alpha over 2. Okay. Now we go step by step. We find actually T alpha over 2 with 95% confidence level. Okay, so here the degree of freedom or nu is defined as n minus 1, which is 15 minus 1, right? N is 15. N is 15. So degree of freedom is 14. Then 1 minus alpha, it is given 95% confidence level. So this is going to be 0.95. Alpha is going to be 0.05, right? 1 minus 0.95 is 0.05. And this is two tail area. So one tail is going to be 0.05 divided by 2 which is 0.025. So one tail. That means the area that we are looking for is going to be point, what is it? 95 plus 0.025, right? Which is 0.975. Okay, we're looking for this t, so that the area is 0.975. So from the table, from the t table, we are looking for the t value. So from t table, p, let's look at that, 0.975. We're looking for a degree of freedom of 14. So this value, and 95% confidence level. Okay, so looking at this row, this guy, right? See, same here, t of 0.975. Look at this. Or you can use alpha as 0.05 or use alpha over 2 as 0.025. See, 0.05, or use this value with degree of freedom 14 and 95% confidence level. Okay, so it turned out to be here t is going to be 2.145. From the table, p of t less than 2.145 is 0.975, which is the area. The t value is 2.145. So t alpha over 2, or t 0.025, is going to be 2.145. All right. Here is the way to find c value, c of alpha over 2 and t of alpha over 2. So we have normal distribution and we have t distribution. And we are going to use these two values to estimate, to do interval estimation. Okay.